So hi everyone, welcome to SNAPP seminar series again. I'm Wayna from CMU. I'm going to be hosting today's talk. First, let me just briefly mention some logistics details so to make sure everyone is on the same page. So please mute yourself during the talk. But you are encouraged to turn on your video whenever you feel comfortable, so the speaker doesn't need to talk into blank faces. The talk will be recorded, and it will be also live streamed on. It's also being live streamed on YouTube. So if you don't want to appear in the recording, please just mute yourself. If you have questions during the talk, you can type those in the chat box. I'll be monitoring the chat box, and if the questions are clarification questions that are quick, I'm going to relay those to the speaker. If the questions are more complicated, then you can either wait for the question breaks in the middle of the talks, or like until the end. There will be a Q&A session at the end. Then you can ask the speaker directly. The slides are on the website, and I'll also paste the link to the chat box. Okay, so yeah, that's the logistics. So today we are really glad to have Bert Zwart speaking. Bert is the leader of the stochastics group at CWI Amsterdam and the professor at the Eindhoven University of Technology. So before that, Bert was at the Industrial Engineering Department of Georgia Tech. Bert is the recipient of the Erlang Prize in 2008, and he also won the Best Paper Award of the Informs Revenue Management and Pricing section in 2016. And he has been a area editor at Operations Research until 2017. So Bert has worked on a lot of things. A significant part of his current research efforts focuses on understanding rare events in systems with heavy-tailed phenomena, and on the stochastic modeling and analysis of power systems. To this end, Bert co-organized a special seminar on the mathematics of energy networks at the Isaac Newton Institute in Cambridge in 2019. So today, Bert will be talking to us about blackout sizes in power grids. Okay, so without further ado, let's welcome Bert. Bert, take it away.
Thanks, Wayna. Thank you all for the invitation and for attending my talk. It is really special to see all the names and sometimes pictures. And also this topic, I like rare events, and talking about this rare events is nice because it makes me feel as if it is 2019 and not 2020. So in 2018 and 2019, we worked on this quite a bit. And actually it started off at the previous flu. Well, it was not exactly a pandemic, but there was a significant flu in 2018. And since then we have been working on this. And so yeah, so this question, I'm going to talk about this question: why are blackouts in power grids heavy-tailed? That's the topic of my talk, and this is joint work with Tommaso Nesti and Fiona Sloothaak. They used to be my PhD students, but meanwhile they both graduated. Tommaso, he actually tried to travel to the US in the spring, but it didn't work. Eventually, I extended his contract with 3 months, and that was actually good because he could do the revision of this paper. And he had to travel through Croatia, enter a 2-week lockdown there, and then from Croatia to Turkey, and now he's in the US. And he's trying to get a job there, but the H1s are stuck. But because this paper got accepted in PRL, his company is willing to sponsor an O1 request. So that's good. That's already like a big impact, I guess, of this work. It's nice. And Fiona is a postdoc at the Industrial Engineering department at TUE currently. Unfortunately, both are not able to attend this talk. I'll have frequent breaks for questions. I see also some people that have seen previous version of this talk, and if they feel they're able to answer some of the questions in the chat box, feel free to do so. I will not be naming any names. Yeah, I won't. All right. So, I'm going to talk a little bit about energy networks and blackouts and about heavy tails. This is really the intersection of some of my hobbies. This is why it was like a mind-boggling question for me. And then I am going to explain to you what is the main insight that we found, and then also something about the mathematical model and a little bit about the analysis. Then we talk about some numerical examples, and then we conclude. All right. So why did I start working on this type of problem? In short, it's the energy transition. So like there are all kinds of long-term goals being set. For example, in the EU, there is a target that 97% of electricity usage will be green in 2050. This is a very ambitious goal. Like currently, what is being green is being debated. Like biomass, is that green? So I took this picture from the website of Mark Jacobson, they made predictions on how each country, or not all countries, but how many countries may achieve the mix. And so we see here for the Netherlands, a lot of wind. Like 2/3 should be wind, which I guess makes sense. We have a lot of it. So, all right. But of course, it doesn't make life easier because we used to generate energy using very predictable big generators. And now if we would replace that with sun and wind, you get a lot of randomness. Of course, this is where the probability comes in. That got me interested. So there's lots of variability. So I got this from a slide, I guess, from Stephen Lowe. These are like samples of daily wind generation, and the point is that it is all over the place, and it is on many time scales. You have fluctuations. You have really fluctuation on many time scales. So you even a wind park, because of turbulence phenomena, can drop its output by half in a matter of seconds. And so, and then one day it can be windy, the next day it can't be. So all kinds of time scales, you have problems. So there's more variability in supply. There's also more variability in demand. This is I've used this slide before. This is the Tesla queue. This is an example of a fast charging station where the Tesla cars can charge their cars very quickly. But if you see there are the servers, but typically a Tesla driver would park the car there and then walk back here and then order a fancy coffee and then drink the coffee. And then, it's a complicated queuing system. But the point is that these electric vehicles, even like here, you can get a queue, but there are also more serious situations of queues, like in residential areas where just a few cars can easily double the demand for electricity. So if you come home and you plug your car in, you cannot just expect. So there are very interesting scheduling problems, stochastic network scheduling problems there as well. I'm not going to be talking about that today, but it's just I just want to. If you have questions about that, it's probably best to send me an email. I can send you references. All right. So that's the variability on the demand side. Of course, there will be also flexibility on the demand side. Sean Mine and Anna Busic have worked on pools. Pools, especially, like they have to be cleaned once a day, and it doesn't really matter when. And so you can schedule it based on the demand for electricity. The same with fridges. So I'm a Celsius oriented person. So our fridge currently is hopefully at 4 degrees Celsius. But if it goes up to 5 or 6, it won't kill me, right? With most dishes, at least. So there is flexibility in demand, but also more variability, especially from because more bigger machines will be using electricity. Then there are also there's also variability in prices. So prices this is an example of electricity prices. So one significant thing is that you see prices can become negative. So you could argue, like, instead of geometric Brownian motion, you can just go back to ordinary Brownian motion, but that's not very suitable because you have a lot of big spikes. So and so, like, well, European markets are fundamentally different than markets in the US. You also see similar phenomena in the US, and so everything is more variable. And then so this is like, these are three challenges where variability is challenging in itself. But there are, so these are like phenomena interesting maybe for probabilists, applied probabilists, but there are lots of other parts of applied mathematics where that need to be developed further. So there is this, in the pre-Trump area, this is very nice document. Many people, I think Dan Beanstalk was one of the people involved in writing this. You can still download this for free, I think, from the National Academy's website. So this is kind of like a quote. So in this report, they identify lots of prediction machine learning questions, but also lots of nonlinear dynamics and control problems, and also lots of optimization problems. So I would say that on the optimization side is very popular. Yeah, you have the AC optimal power flow problem. There was a competition, must have finished by now, where there are these very difficult high-dimensional stochastic non-convex optimization problems that many people, especially in the US, work on. Because it's sometimes to decide even when to schedule maintenance is an extremely difficult problem if the system is very highly utilized. So in Europe, the grid is working a little bit better, and we can still linearize the physics for the most part. And so these type of optimization problems are less critical in Europe, I think, for the moment. But I mean, I don't want to go into this further. But yeah, so these problems don't go away. The physics cannot be changed, really, fortunately. And so lots of interesting problems. So when I started getting into this energy, let's say, business for field, the question really was, what am I going to work on? So I'm not an optimizer, I'm a probabilist. So you can, of course, try to include probability into the optimization, but I would say that I'm also probably a little bit more of a scientist than an engineer. So I'm really more intrigued by questions like, how does something work? Or why is something true? Rather than this is like the more cardinal question for me. So this is a photoshopped image. There are better images from NASA, but this is so what happened here. This was a blackout. Happened on August 11, and it took about 4 days. 55 million people were without power at some point, and to resolve it took 4 days. So Dan Beanstalk told me that he started working on blackouts because he was in the dark for 4 days and he had nothing else to think about it. Like, how on earth did this happen? And he wrote a very nice book for operations researchers. I can highly recommend you to have a look at it, or even buy it. He will be happy. So, yeah. So this is an example of a big blackout. So what happened was that. So first of all, it took years, or it took a long time before they figure out what happened. This is typical with blackouts. So typically, if they figure out what happened, and that typically is usually weirder than any movie script. So in this case, a line got overheated. So if a line gets overheated, it sags and it hit a tree. But then, I mean, this happened more often, but then you detect it. But in this case, there was some software error. So they thought something else was going on. And the software started some automated control actions. So they were doing the wrong things. And one thing led to another, basically. And then I think the biggest problem was in Ohio, which, sorry, excuse me, I'm from Europe, but I think it's not here, right? Ohio, it's more like over here. And so then the electricity that had to go from here to New York couldn't go here anymore. So it had to go all the way around the other side of the Great Lakes. And then everything went black. And So this is just one blackout, but there are more often blackouts. So this is a slide with a bunch of blackouts. So I didn't make it. This company DNVGL made it. So India has, of course, the world record. Well, of course, China could do better potentially, but they didn't. They have not achieved such a big blackout yet. The Netherlands, the little blackout here, March 25th. So this goes up to 2015. And in 2018, we had a blackout at Schiphol Airport. In 2017, at the Lunteren conference, we also had a blackout. The trains didn't go, so everybody took a cab. Yeah, I mean, but still, these blackouts happened. This was an interesting blackout in 2006. This started in Germany, so even the Germans are not free of blackouts. What happened here was that a ship wanted to pass through a canal. It was a very big ship, so they had to shut down a high voltage line. The ship was 2 hours earlier, and so the skipper called the electricity company, asked for permission, and said, "Sure, you can go." But the person who was operating the German network didn't know that it was very windy in Poland, and in France they were buying the Polish wind energy. So Germany, all the lines were needed at that point. So the N-1 criterion was not satisfied. So Europe got split into 3 islands at that point. And so there are like all kinds of blackouts. And there are all kinds of sizes, and every blackout is a unique story. I can spend an hour talking about these stories, but like every blackout is a unique story, kind of. So when I talked about doing this type of research, there were some. Before I go on, like, let me tell you that there are also. So normally, what you do is so like what people are afraid of, why these blackouts are also more important than ever, is the increase of renewables, which add variability in the system. So normally you want to keep your system N-1 secure, which means that you have a list of contingencies and you check if any of these contingencies happen, whether you have system stability, yes or not. And this basically means that you're computing a solution of the power flow equations, and you check if all the voltages and currents are acceptable. And if not, you need to do something extra. And so this violation of the N-1 criterion maybe happened 3 times a year in 2003, but nowadays this is old. It will not have gone down. Like the criteria is not satisfied on a daily basis. And so this more or less means this is due to the fact of the renewables, but also because they solve every so many minutes a planning problem as if it is a deterministic problem, and it is of course not. So they're like the separation of timescales for like problems, it no longer holds. So they need to do something about it. But of course, it can lead to more blackouts too. Why not? So yeah, this is a final example of where renewables were being blamed. This is one from South Australia, where they had rolling blackouts. Of course, we had rolling blackouts in Los Angeles this summer. For those of you who follow Michael Schellenberger, he was very angry about it, and he blames the renewables, and many people do. So I think the problem with California is that they're in one time zone, and what you could do is put a big high voltage cable through the Rocky Mountains, and then you can get like states from different time zones balance out supply and demand. But then the problem is that each state has to agree. And there was an interesting article in Scientific American 2 years ago why it will never be possible to have all these states agree. But let me not get into the politics of that. And so let's go to the mathematics. So all these blackouts have all kinds of special stories. They are beautiful anecdotes, but like the question is, can we do anything scientific? Like they're all unique anecdotes, right? So the most recent significant blackout in the Netherlands was Schiphol Airport was suddenly without power, which is of course bad, because then no airplanes can fly. And it took TNO about 5 months. TNO is the Dutch Applied Research Institute. They were told to come up with some preliminary conclusion within 5 months. But this TNO is more like a consulting firm. So Tenet, which is the network operator, yeah, I don't know if they already have an official conclusion, but they have like maybe an unofficial one. But it can take years before they find out. So also in 1996, there was a big blackout in the US. I think that one took 2 years to figure out what happened. So, like, I talked to several people. I will not be naming names, but like some people I really respect. So somebody said during a talk, like, blackouts are not complex, but complicated. And what does this mean? Well, in a complex system, you try to understand macroscopic phenomena from microscopic interaction. So you have like complex systems have some nice, beautiful emerging behavior. And so the argument there was that like a power grid is not a complex system, but a complicated system, kind of. It's just like such a weird. So similar, like when I wrote this proposal for the Cambridge semester on energy networks, I thought, okay, we should have a focus period on blackouts. And somebody wrote, I would support it, but I don't think it's possible to come up with a both interesting and useful result. So this is what you see is that lots of the mathematical models are extremely simple models. And like a branching process, for example, and there is no real network there. And the other end, the engineers, they have gigantic simulation models, and it seems hopeless to do any math there. So perfect problem to work on if you have tenure. And the more people said that there's nothing there, the more stubborn I got, of course. But I ask, like, my question is modest. It's a scientific question. Like the title of my talk is "Why Are Blackout Sizes Heavy-Tailed?" And so that is the feature which I do not find complicated because I happen to work on this. So you see what you see in power grids. If you look at the blackout size, either in how much power had to be shut off or the number of customers that got affected during the blackout, you see this nice power law. Yeah, so you make a log-log plot. And you get a nice straight line. And lots of data sets are being sold as power law, but this one seems to be rock solid, passing good statistical tests and so on. So I was quite convinced that is a power law, but the question is, of course, why? So this is kind of the intro. I don't know if there are any questions up to this point.
So there's a comment from Alan. He said he actually asked Jay Pat from our electricity center why the rolling blackouts in California. He said it's still unclear, but his early opinion was reduced hydro generation from Northwest and correlated NG plenty failures. They are correlated due to increased failure rate due to high temperatures.
Yeah,
I actually don't know what NG plan is, so NG plenty, but that's Alan's comment.
Okay,
natural
thanks.
gas.
Natural gas. Okay, yeah.
I see.
I mean, the natural gas was also a problem in Adelaide. I think in Adelaide they don't have a day ahead market. And natural gas, if you wanna order natural gas, they need a couple of hours to start up their factory. So if you don't have a day ahead market, and you just say, "Oh damn, we run out of electricity, start burning," then say, "Yeah, it will take 3 hours." So then, yeah, so in that case, okay, Musk delivered a beautiful battery and it works, but Shmuel is there too. So it's kind of like complicated, but all right, let me move on. So the goal is to come up with a mathematical model that explains why blackout sizes are heavy-tailed, and the model should be sufficiently structured that it has some resemblance of a model used by engineers. So like branching process, or like that's too simple. That's what we felt, and we would also like to get some insights in the way big blackouts occur. So then the question is, of course, then can we use this to reduce the likelihood of big blackouts? And another question which I will not answer today is, will the number of blackout increase when we have more renewable energy? It's kind of like a long-term question. All right, and so blackouts in a power grid are non-trivial because they don't propagate according to nearest neighbor principle. It's like if you have one line failure, the line will essentially be removed from the network, and then the physics will reallocate the power flows in ways that can make things look very predictable. So that this is why it's a non-trivial, also why it's a non-trivial problem. So I'm going to, because I'm quite talkative and we are halfway, maybe a little speed up a little bit. So say a little bit about tails. So the blackout size apparently has a Pareto distribution. So a Pareto distribution is an example of a heavy-tailed distribution. And if you have heavy-tailed distribution, extreme values are relatively frequent. So Pareto was an economist who actually studied income inequality. So like, for example, now Jeff Bezos has 200 billion, and it's a lot of money. And if he would attend this talk, we would all be a billionaire on average, right? But if he would enter the Zoom box, we would not be twice as tall on average. So for length, this is a typical situation where you better use something like a Gaussian distribution. And you have like a typical the length of a human being is centered around a typical size, 5 feet or 6 feet, while wealth can be anything from 0 to 200 billion these days, and next week it's probably 300 billion. All right. So
David has a question.
Who?
David, you can go ahead and ask.
Sure. Hi.
It's good to see you. So kind of a high-level framing question. So is the general thought here that blackouts are due to us not having efficiently enough structured the resources we have as far as like what our power system can do? And
I'll get to this.
Okay.
I'll get to this.
Okay, and just the high-level analogy was like, right, a question that comes up sometimes is, after we do all the machine learning and algorithms in the world, will there still be traffic jams? Or is this...
Yeah, there will still be traffic jam. Yeah.
Okay.
Yeah, but
okay,
I'll get to this later. More philosophical. Yeah. All right. Let me continue. So, so what we call this, like in light-tailed distributions, if you have like a certain system-wide rare event, these arise because everything goes wrong. While in heavy-tailed cases, you just have a few catastrophes. So light-tailed large deviations, large deviations theory and extreme value theory are kind of like the techniques to analyze these type of events in probability. And so light-tailed is already more than a century old, while the analysis of heavy-tailed distribution maybe only half a century. I think Chichtakov was the first in 1964. Of course, there is the work of Levy in the 20s, but it was more like central limit theorem type of problems. All right. So these are the three standard examples, Pareto, log normal, and Weibull. And we will be mostly focusing on the Pareto in this talk because the blackout size has a Pareto tail. So the key properties of heavy tail distribution is that there's no moment generating function, no finite one. The probability that the sum exceeds some large value is roughly equal to the probability that the maximum exceeds some large value. So this property is going to be needed later on when I explain some heuristics. All right, so heavy tails are everywhere, but heavy tails kind of like, they're not that interesting. I mean, you could argue that they're not interesting because you can transform any random variable using some transformation into a heavy-tailed distribution. For example, the exponential. If I raise it to the power e, I get a Pareto. So the question is, so what? And it's a justified question. Of course, in the context of blackouts, like, they're very close to having an infinite mean. So the cost, if you assume the cost is linear in the size, the big blackouts are as costly as the small ones. So the big blackouts do matter, and so there the power law kicks in cost computations. But putting that aside, like the more interesting question is I would say, why does this occur? And maybe we can learn something from it. Maybe we can understand something. So I'm mentioning here some other examples: computer systems, finance, social network, and there are like answers there. So in computer systems, okay, allow me to abstract it away with a queue. So why, if you look at a multiple server queue, so the question is, why does a large queue length or why does a large waiting time occur? And so the answer is due to several big job sizes. So in a tail analysis context, the Pareto case fundamental contributions have been made by Sergey Voss and Dima Korshunov. Earlier, Alan Scheller-Wolf has, of course, he's there, and I didn't put him on the slide. This always happens. Sorry, but Alan already in his PhD thesis identified phenomena very similar to it. That the waiting time can have more finite moments than a service time if you have a bunch of servers extra not needed for stability. So the more slack you have in the system, the more finite moments your waiting time will have. And so recently we have resolved the Weibull case in a paper that you can find on the archive. But so the bottom line here is that, well, in a single server queue, it's very simple. The waiting time will be large because of a single server's time will be large. So it's really like the output of the system is heavy-tailed because the input was heavy-tailed, and the dynamics of the system itself didn't do a lot. In a multiple server queue, it's slightly more complicated. That dynamics do it, but if you have a light-tailed service times in a multiple servers system, you get also light-tailed queue length and light-tailed waiting time. So the dynamics of the system cannot create the heavy tails. It's really exogenous heavy-tailed input that is the root cause of heavy tails. All right. So of course it's not always like that. It is like that also in lots of actuarial models, but it's not always like that. So in math finance, I once made this joke that Harry Keston was famous for his work in math finance, but of course he's more famous for his work in percolation theory. But this is one of the papers. He sadly passed away last year, and so my colleague at CWI, Rob van den Berg, was a collaborator of Harry Keston. He wrote a very nice. There were several obituaries, but Rob van den Berg also wrote one, and he actually didn't quote this paper. But like so. This is, I think, a very important paper. It's very difficult to read. Keston was able to come up with he was able to start a proof with a couple of very bad ideas, and then he was so good that the proof still worked in the end. That was apparently the anecdote about him, and this is an example. So Tomasz Mikos, I don't know if he's here, but he and two colleagues from Poland, they wrote an entire book attempting to understand this paper. I think they write in their intro that they didn't reach their goal, but their book is very nice, at least. All right, so what is the result? If you look at the stochastic equation, then under some conditions you have a power law, and the condition is that this kappa solves this equation. So A has to be bigger than 1 with some positive probability. So the takeaway here is that heavy tails occur by multiplication. So why is this important for math finance? The ARCH models that came in the beginning of the 90s are more or less a transformation of this equation. So this is why it's important in math finance. So the takeaway is that the nonlinearity causes the heavy tails here. So in networks, you have, I mean, this is the paper that got this famous, but there are papers from 1955 and already Yule in 1924. Had this preferential attachment, but he called it differently. So you have the rich gets richer phenomenon. So in networks, so if you have this preferential attachment mechanism, you see, so the way it happens is that a network is growing, and then every new node connects with a certain probability to existing nodes. The probability is then proportional to the degree of the links. So this also creates power laws. So actually, some shameless. So this is a copy from the book I'm writing with Adam and JK. Adam is in. I'm supposed to send some updates. I'm sorry, Adam. I'll do tomorrow. He's in the audience. So don't keep him on mute, please. All right. So so the takeaway here is that the power law degrees are created by this preferential attachment mechanism. And so final example is the branching process. So this is a critical branching process. So we know that if we have a classical branching process and the mean offspring is 1, we know that the branching process dies out with probability 1, but the entire size of the tree and also the depth of the tree, they are both heavy-tailed. Actually, in this case, they have an infinite mean. And so this critical phenomenon, like you have like many systems are argued, especially by physicists, to be in a self-organized critical state, which basically means that like the system is self-organizing in such a way that it pushes itself to the edge of criticality. And actually, this was the most popular explanation in power systems, because which has been popularized and by Ian Dobson, wrote also many papers about it, and it is intuitively kind of obvious. So the power system, like like the equipment is very expensive, and so you have to earn it back, and you want to use everything as efficient as possible. So that was kind of like this is, I guess, still the mainstream explanation for power systems. So, but the takeaway is that this heavy tails can occur if system operates in a critical regime. So, of course, I forgot to say a few things. So Søren Asmussen has a nice, and other people have worked on the restart algorithm that also can induce heavy tails. And there are all kinds of, so John Doyle has the HOT mechanism, highly optimized tolerance. This is also suggested for heavy tails. That is more like the input causes output. And I thought about all these phenomena. Like I did my PhD on heavy tails. So like when I thought, okay, what is a good problem in a setting to work on? So like, this is it. Nobody has a clue what to do. I have tenure, so think about it. And we did, I mean, so with Fiona and Tommaso, we were a great team. So Tommaso was very good in doing lots of numerical computations, and he knew the microscopic model of the power grid pretty well, while Fiona was more into heavy tails and power laws and into macroscopic phenomena. So we did a lot of simulations, and we tried to, so like the papers that Ian Dobson wrote about the organized criticality, what he does is that he has a very big simulation model, the OPA model, and then he has traces, and he shows that there are long-range correlations in the traces, and then he says, okay, and then he simulates a sandpile model. This is like the canonical model for self-organized criticality. And he says, okay, the simulation traces look similar. So it is self-organized criticality. So like as a mathematician, I was not very happy with that. I want to get it from the same model, right? So I don't want to use analogies. I want to have like endogenous explanation. And so we did a lot of simulations, and nothing worked. And so then actually that was in 2018. So I was in March. I was in Berkeley. There was a very nice workshop in Berkeley organized by David Smoysh and others at the Simons Institute. But for most of that, like I was the first speaker of the first day, but for most of the workshop, I was ill in my hotel room, and then like for 10 days I was there, and I was feeling miserable. And then I flew back. And I got really ill on the plane, and then I somehow managed to get home. And then my general practitioner wasn't there. And 1 week later, I wanted to have some tests, but as you know, probably we don't like tests in the Netherlands. And so the assistant of the general practitioner basically says, you can't come for a test because like it's probably not that bad. And then I had to negotiate to come, and then like the general practitioner couldn't see me. Then it turned out that I had pneumonia. And so I had pretty bad pneumonia, and I was in bed for 6 weeks, and I had nothing to do. And at some point, I got on the Wikipedia page on German city sizes. So, and then I was shocked. It was just out of pure boredom. Who cares about German city sizes, right? So there I saw it, like Berlin is twice as big as Hamburg. It's 3 times as big as Munich, 4 times as big as Cologne, 5 times as big as Frankfurt, of course. This is the zip flaw of city sizes. Many countries have this phenomenon. At least many Western countries. There are African countries where it's not true. And then this kind of like hit me like, this should be it. And so, so I actually went to the paper of Clauset, Newman, and Shalizi. They have a table of 24 data set with power laws, and I looked at it for the US, and the index of the power law is practically the same. It's way within the confidence interval. So we got a better data set. We got a better, more recent data set compared to this paper, and we did some more statistical analysis. And I don't have time to get into that, but the hill plots, they really intersect many times. So the hill plot basically means as you order your data from small to large, and then based on the largest K data, you estimate your power law using maximum likelihood, and then you plot it in terms of K. And then if you use all data, you get a bias. If you don't have enough data, you have too much noise. But you cannot use all data because the tail typically it's not Pareto everywhere, it's Pareto in the beginning. And so the reason why it should be the same power law as the city sizes is pretty intuitively pretty obvious. So you have a network which is balanced, supply equals to demand, then some disturbance occurs, it induces other disturbances. The network breaks into two pieces or more. One piece has a surplus, the other piece has a shortage. Now let's focus on a piece with a shortage. That piece with a shortage is a certain region, and the total demand in that region is proportional to the demand of the cities, of the city sizes. Like the city has people in it, and I assume that everybody roughly has the same demand on this scale. And so because there is a shortage, because of the Pareto, the nature of the Pareto tail, you have very big overshoots. The shortage will be proportional to the total size of the region, but the total size of the region is the sum of the cities in the region, and the sum of the cities, because of the Pareto, is equal to the maximum. So at the first time that your network breaks into pieces, this sum is equal to the maximum phenomenon of Pareto distributions should already be enough to get a power law. That's the intuition I had. So then the question is, of course, I mean, can you prove that in a model? I'm a mathematician, but you also have to do simulations. So that's what we did. So we actually, this intuition that I described, there are some caveats. I will try to get through them, all of them. And I'm not quite sure, like, if people are already convinced, but at least I have the feeling I understand it. So here is our mathematical model. So I'm going to look at the graph where I assume the topology of the graph is fixed. I have n city sizes. There will be edges between the cities if there is a high voltage cable between them, or line. Sorry, cable means underground. I often make this mistake with engineers. Anyway, there are like edges. All right, we're all mathematicians here, and so the edges are fixed, but the sizes, the capacity of the edges have to be determined. They're going to be part of the model. So what I'm going to do is it's a similar trick as the random graph community uses. I'm going to deliberately keep part of the system random. What I'm going to keep random are the city sizes. It kind of doesn't make sense because New York will not be the size of Ithaca. We will not resample New York and Ithaca on a daily basis, but this will be a static model where I prefer to keep the city sizes random. Okay. Right, so to model the electricity, we used the DC load flow model. We have done some numerical experiments with AC as well. But for now, we use the DC load flow model. If you don't know what it is, it's linear, so you can do nice math with it, but it's not always very suitable. But at least it's better than a branching process. And so then you have the network topology and the line reactance. They're all encoded in a certain load flow matrix V. And now, if I am assuming that I have a static model, so I assume that the demand from each person in a city is equal to 1 unit. I don't even talk about what is the unit here, right? So the demand is 1, and so the supply vector that will be part of the model is going to be some vector G. And then if we know the supply and we know the demand, and then these are going to be the power flows. Now so this is already part of the model, but we have more elements in the model. So we have 3 stages in the model: a planning stage, an operation stage, and an emergency stage. So the planning stage is more like a network design stage. You should have called it a design stage. So they're like, so our model is an abstraction of reality. For example, it's static. Of course, it cannot be static. So I got this from a slide of Kostia Turitsin. I don't think he is here, but I thanked him for it. So this is so like there are lots of time scales here. So network design problem. So the model of Ian Dobson is dynamic. So he really has this expansion planning based on failures in the past, and he has a very nice loop that is more realistic. But he has simulation. So in the future, I hope to look at this more realistic model as well. But like just we are roughly, the design will be roughly here, then the operation will be roughly here, and then the failures are at the lower end. Okay, so let me begin with the middle one. The operational stage will be a DC OPF problem, where I'm not having any generation constraints in this simple version. Of course, the referee asked us to do the simulations for this, and we did them, and we still see the same phenomenon. So you need to solve, this is a DC OPF problem, and you minimize costs, generation costs, subject that supply is equal to demand, and subject that the power flows do not cross certain safe boundaries. And the boundaries are given by this vector F bar. Now the F bar, we're going to determine the F bar in the design problem. So the design problem, I mean, honestly, we just cooked this up because we could do math with it. We could prove a theorem with it. And yeah, this is the first theorem in this context. So like, we hope in the future make it more realistic. But so the F bar, we just simply solve an unconstrained OPF problem where we, yes?
Sorry to interrupt, though. Quick question. What does DC OPF stand for?
OPF is optimal power flow. So this is a very, this is the type of optimization problem that is being solved every so many minutes for planning purposes. So it's an optimization problem, and so there is the supply here and the demand here, and you see that the flows here are a linear function of supply and demand. And in the reality of the physics is that they're very nonlinear. They are the so-called AC equations should be used, but this is the DC approximation of the AC equations. So the DC is a linearization of a more complicated physical model.
Okay, got it. Thanks.
It's not a direct current. It's a, yeah. Okay, thanks for asking this. So if you solve this toy OPF problem, you get actually a solution that every city should produce the average. And now what we do is we set lambda as a safety parameter, and we compute the line flows as if we produce the average everywhere, and then we put a lambda in front. We can generalize this to weights here, but then you don't get the average, you get a weighted average. But we could, the math would still go through if we would have constants here. But that gives us the line flows. And then we have an extra lambda there, and this is what we will do for our OPF problem. So the OPF problem now will look like this in the operational stage. So we solve OPF subject and where we use the line flows here. So all the time, so these x's in our models are random variables, but you can just freeze them and solve them if you want. So this actually gives us the actual line flows. You could add lots of bells and whistles to this, but this is the simplest version. Now we're going to break stuff. That's the emergency part. So we toss a coin, and we're going to break randomly a line. We start with one random line outage. If you want, you can start with multiple outages or other types of outages. That's not really crucial for our math to work. You start with one random line outages, then you remove that from your matrix V, this line. You recompute the power flows, and then if additional lines then fail, if a new line flow exceeds the upper limit, where you don't use the line flows in the OPF problem. You use this safety parameter. So you're allowed. The OPF usually has a little bit of slack. This lambda is a little bit less than 1, so you're allowed to break it a little bit more. That's this flexibility you have, and you continue. So if islands occur, we assume that load generation is shed proportionally, and you continue until the cascade is over. And T is the size of the total load shed, which in our model, because everybody needs 1 unit of energy, everybody has, so this is the side. So yeah, why did we come up with this? We were managed to prove something. So it's kind of crazy that we're able to prove something for this. Most people said, like, don't even try. The reason is that, so the city sizes here are random, and then the line flows are also random, but you can come up with representations for the solution of the DC OPF problem here that you can work with mathematically. So the point now is that if X is a generic city size and T is the blackout size, what we were able to prove is that the blackout size has a power law, like the city sizes, where this constant is equal to this. So it's a beast, but you can compute it if n is the number of lines and m is the number of nodes, you can compute it in n square m time, this constant.
Bert, question. When you say that you remove a line from the V matrix, V is the BB inverse. It's based on the reactance matrix. So you cannot just take out the PTDF when you remove a line. You have to reinvert the B matrix.
You're right. But I was sloppy in my words, but in the paper we do it the proper way. But yeah, you're right. Yeah, I was a bit sloppy in my wording. You have to recompute the power flows the way you describe it, and that's what we do. Okay, thanks. So the crucial idea of the proof is that the heavy-tailed large deviations theory tells us that we only need to consider the case of a big city and many small cities, and then you can do a renormalization argument. We got a lot of flack for that from the referees, that like one city is equal to 1 and the other cities are equal to 0. So now if you look at the special case of our model where one city of size is of size 1, this is a continuous approximation, of course. You can also say one city is of size X and all the other cities are of size 0. In that case, we can do the computations quite explicitly. We can compute the solution of the optimal power flow explicitly, and we can actually track the cascade explicitly. We can kind of come up with an algorithm to keep track of the cascade sequence. But then the problem is that the cascade sequence is a discontinuous functional. If I tweak the demand, if I increase the demand somewhere in the network by epsilon, I could get an entirely different cascade. It's a discontinuous functional, and but since we have uncountably many lambdas, but only finitely many sequence, we were able to prove that this sequence is stable for almost every value of lambda. So we have, like, for almost every lambda, we have this stability, and that actually, like, this actually cost us 6 more months. I didn't want to write. We were first considering to write a paper and say this should be the constant heuristically and not proving anything, but then you run the risk that somebody 5 years down the road actually proves that there should be a sinus function in front, and then that would be terrible for a mathematician, of course. So we really wanted to be precise, but took us 6 months to do that. And so I'm not going to say more about the proof, but that's kind of like what we had to do, and you can look in the archive to see how this works. So this is just an yes.
Question from Kathy. Is there any assumption on the green network structure?
No, not really. Well, it is not an island. We don't begin with an island, but the grid network structure is fixed.
Okay, thanks.
So actually, so the paper has been published at Physical Review Letters because we thought, I don't know, like, I sometimes make these jokes at the expense of physicists that the math is too easy for a math journal, and the model is not realistic enough for an IEEE journal, but the insights are really nice. And so this is why we thought that the physics journal is appropriate. One referee thought, your intuition is so simple, why do you even bother proving a theorem? And actually, I also had a chat with Peter Glynn where I explained to Peter that we did lots of simulations and we proved the theorem. He said, like, was it worth doing? And I naively thought he meant, was it worth doing the simulations? But he meant, was it worth doing the theorem? But I did feel like it was worth doing. Yeah, somehow. It's just, I just adhere to my own standard, and I just wanted to be sure that it works. And so it's not totally trivial that this blackout sequence is always stable, and we still don't know what happens at this critical point. And I also think that the whole analysis shows that the situation is pretty robust. So it's really the input. The city sizes were already, like the city sizes are so disparate in size that no fancy network structure will help you fix this problem. That's kind of like the message. And so this is an example of a simple cascade, but it doesn't add much, but I'm going to skip it. But for some certain networks, you can actually show where the phase transitions are. So in this picture, it is at 1/4 and 3/4. And we are able to show a conditional limit theorem, like given that a very large blackout occurs in our model, which line failed first, and you will typically see it's are the lines close to the big cities. So it's also like consistent with a study of Adilson, Motter, and colleagues, that they also show that the lines close to the big cities, they are the most vulnerable ones in blackout. So like our insights is consistent with what they found in that paper through simulations. Okay, so we did numerical studies. Generation, we included generation constraints, extended for some IEEE test networks, the DC to AC, see what happens. We actually rerun all our simulations, replacing the heavy-tailed city sizes with uniform distributed city sizes. There is a nice topology generator from all the intersections of complex networks and power grids, because the power grids, they are not a small world type of networks. The degree distribution is not heavy-tailed, but there are like modifications of the Watts-Strogatz networks that you can use to mimic power grids. So we ran simulations for that. But I would say that the most critical assumption, that like the elephant in the room, is that we do not resample the sizes of New York and of Ithaca. They will always, one will always be big and the other will always be small. And so I had a chat with Ian Dobson about this, and he also said, like, okay, so and he's right, is that what we basically say is that like a blackout is a bootstrap sample of a city size. And you know that like with bootstraps for heavy tails, is that if you have your bootstrap size too large, you will not see the detail anymore. And while on the other hand, in the US, we have a data set of about 2,000 failures of blackouts, more than 15,000 people affected, while we have like the number of cities in the US is way bigger than that. So in the US data, we don't see this problem yet. Maybe a million years from now, well, there will probably be other problems by then. But like it really only works. So we see that we have the side grid model of Germany. We've run simulations with that, and we did simulations, and we don't get power law phenomena there. So in Germany it's very simple. Like if you have a big blackout, either Berlin is cut off, the Ruhr area is cut off, or Munich is cut off, or Hamburg is cut off. That's it. And so the network somehow is too small to see power laws in the data, but you do see principle of single big jump coming back in the blackout. So you typically see one, if we run simulations, you see one point where there is a gigantic load shed, and there are like a few aftershocks. And I was at the IEEE conference in 2017. It was right after the APS conference. It was in Chicago. And I did a tutorial on how industry copes with power grids. So Idaho Power, Miroslav Papic from Idaho Power, he gave a tutorial, and we were allowed to play with some of their software. And I was also frantically playing, and like I tried to actually get a very big, heavy-tailed branching process out of their software, and I couldn't. It was always in the third layer. The entire of Idaho was done. And so you don't see these deep trees as you would get in heavy-tailed branching process. Besides, the mean of a blackout size seems to be finite. If you go back to the hill plot. So what they did in the old days, if you look at the first paper on blackouts, they use all the data, and if you use all the data and you would fit a Pareto distribution, you get an infinite mean. If you do it in a better way, you only use you have like all kinds of dynamic ways to choose the cutoff point. You clearly see a finite mean, and so branching process has an infinite mean, but doesn't have a finite mean. So kind of, it's, I think, hard to sell the critical phenomena if the mean is clearly finite. All right, but of course more work has to be done. Another point is that, so we didn't prove anything for this frozen versus random city sizes. If we want to prove something, so we did do simulations of networks. The Wang-Scaglione network of size 10,000 on a supercomputer. We did simulations, and then we were able to see the heavy-tailed blackout sizes on these huge networks. But like the German network is simply too small. And unfortunately, we don't have a very detailed representation of the US grid to play around with. But that was also something to do for the future. All right, let me wrap up because it is time. And I'm already over time, and there are probably questions. So I would say that the major insight is that the problem is already at the input, and we just have to live with heavy-tailed blackout sizes. You can, the constant in front, so the alpha is very robust. The constant in front will really depend on the model assumptions. So this single big city heuristic, you can plug it into a much bigger model and then try to get estimates of the constant and then try to come up with algorithms for capacity expansion, but it is way too early to suggest if this really works. But it could be, it's something that I want to pursue maybe in the future if engineers would be interested in this type of heuristics. But then the model has to become way more realistic. But then we don't have to prove anything, so we could still pursue it. So I already said this. Oh yeah, one thing which is kind of suggestive because we didn't really do research in it. But if you look at the duration of a blackout size, duration is not a Pareto tail. It's as a Weibull tail. It's a much lighter tail than a Pareto tail. So at some point, like if we cannot prevent the network, I mean, you can upgrade it all you want, but there will always be some kind of contingency that will cause it to go to be disrupted. So at the end of the day, we have to survive locally. And since the duration, it may seems to make more sense to invest in ways to survive a blackout of a given duration. I don't say that we should invest all our money. This is not part of the research, but I just saw this from the data. And so given the fact that we cannot change this power law phenomenon by making a better network, this might be an alternative to spend part of our money on. And so finally, this seems to be a new class of network models. This is the mathematician talking. And also, like networks of highways, they're also not scale free. So then the question is also like, what can we see in highway traffic? So our national records in the Netherlands was 1,500 kilometers of traffic jam, and then we broke it, and it suddenly was 2,200. And this, of course, an anecdote. It's not science, but it's kind of interesting to see which other networks can be studied in this way, where you do see scale-free phenomena like sizes of traffic jams, but the topology of the network itself is not scale-free. But you have the city sizes that might be responsible there. All right, that's it. I'm now open for questions.
Yeah, thank you so much, Bert. Shmu raised his hand very early on during the talk, so maybe I'll let him ask first. Go ahead, Shmu.
Yeah, so you seem to ignore the fact that the way, you assume that the lines are being opened at random rather than what's the engineering strategy that you use islanding strategies. So when there ever is a failure, the first thing that they try to do is to island, to partition the network, so it's more systematic rather than random.
Yeah, so I don't have an early. So what you could do is, like, if there is one failure, you can do some strategic islanding to make sure the blackout doesn't even happen. I agree that that this is not in the model. This is a weakness of the model. But I would guess that this, if you put such a thing in the model, you can significantly reduce the pre-factor, but there will always be sets of contingencies where islanding won't work.
Yeah, because that's what self-organized criticality is trying to do, to try to capture also the fact that there is a human intervention there that determines the size. Like if you look at distribution of forest fires, you look at distribution of file sizes in computers. The self-organized criticality capture the engineering side, that those things.
Yeah, but if you look at I agree, but if you look at the OPA model, the human intervention is to decide which line to upgrade after previous blackouts happened. So this is not on the time scale of islanding. And so also another thing, city sizes have been heavy-tailed since 1906. And so by that, in 1906, we already had heavy-tailed city sizes. So this is when we so if you want to initialize the model of Ian Dobson, you have to go back to the beginning of the high voltage grids in 1906. The city size were already heavy-tailed then. So then you need to design a network for the first time. And then you would, so what I would argue is that if you would initialize the model at the beginning of the 1900th century in my static model, and then you run Ian's dynamic model, then both of our models will be consistent. But this is a speculation at this point. But I think in the end, the two, and yeah, and so I think so the human intervention, I agree, but you could also argue that city sizes are heavy-tailed because of a self-organized criticality, right? So it's it's very hard. Where does the human intervention begin? And so all what I'm saying is that the cities were already there, and I think the islanding, there are lots of things that humans do, but yeah,
when you're using synthetic networks, which there is now a collection. We have synthetic networks up to 80,000 nodes, because ARPA-E had this project, and so those synthetic networks don't take into consideration city sizes. They are being based on, I don't know, what criteria, but if you look at the Tom Overby synthetic networks, and you're going to use those in your model, I'm not sure that will correlate with any city size.
Well, the point also that you didn't raise yet, maybe you were planning to, is that, of course, a single node in a high voltage grid doesn't correspond to a single city. So, for example, in the German in this German network example, the side grid example, there's now a European version. We didn't do anything with that. We had to go to a geographic information system and see in which part of which region everything worked. And then we did Voronoi tessellations on top of the network. And then, of course, Berlin has not one single node. It has many nodes. And so that also, that's another abstraction of our model. So I would say in the end, that what our model is achieving is an endogenous explanation on why blackout sizes are heavy-tailed. And it's the first endogenous explanation. If you want to, actually, the problem with self-organized criticality is that I asked a mathematician working on self-organized criticality, what is it? And then they come up with a sandpile model, but the sandpile model is just you have 4 grains of sand and they topple one in each direction. But you can also say you can also have a more general toppling mechanism. So the criticality is that the grains of sand are being preserved, and comparing one simulation trace with another of 2 totally different models is not an explanation. And so much more work needs to be done. So like what I really want to do is look at the OPA model and try to prove a theorem about that model, because I agree that that model is more realistic than ours.
Okay, I'll let somebody else take.
Hi, Bert. I have a quick question
Hi.
about the planning problem. So somehow I'm confused about the fact that the graph doesn't show up in the planning problem. And that's part
Excuse
of the reason the graph, the underlying graph structure doesn't show up in the planning problem. Why is that?
It is in the matrix V.
Okay, I mean more specifically.
Oh, you're right. Yeah, it's not in the planning problem. You're right. Yes. Sorry.
And
yeah.
Because of that, like you say that the planning problem has a solution GI equal to the average, and
Yeah.
that's because the graph doesn't show up here. So
Exactly. Yeah.
Shouldn't the graph be present in the planning problem? Shouldn't that be taken into
Well,
account?
the planning problem is of two parts. First, we solve this thing, and then we set the line limits like this. And so this is a mathematical construct for the sole reason of being able to prove something.
I see. Got it.
If we don't do this, we can still construct lower and upper bounds that get the same alpha, but I cannot guarantee the existence of a pre-constant. So this alpha is very robust to get a pre-constant and the existence of a pre-constant. But if you want to get a lim in for a lim sub result, you don't need all this.
Got it. Okay. Thanks. Thanks.
David?
Yeah, so kind of a two-parter, Bert, that are both related to the same thing. So maybe I notationally missed it probably, but does the model account for the fact that bigger cities are presumably more likely to quote unquote be sampled according to your bootstrap methodology, just because New York is maybe so complex that yes, it is a bigger city, which maybe affects raw units of power involved, but presumably the complexity also, like it's very likely to have an outage there just because of the complexity. And then the related question is, when we talk about distribution of blackouts, what do we really mean there? And to make sense mathematically and kind of conceptually of the results here, does this include my individual house losing power? Is that a hyperlocal blackout? Should that be counted to conceptually make sense of a quote unquote distribution of blackouts, and how to think about that and as it relates to the first part?
Well, I don't see the relation, to be honest. But I mean, so like the question is, I mean, of course, if you have a blackout for 30 seconds, does it count? And typically in practice, you need to be cut off from power for at least I don't know what the standard is, maybe an hour or 20 minutes, I don't know, but it depends also on the country. Whether New York is sampled more often, I mean, that I guess in our model that yeah, I mean, if the biggest, like within our model, the biggest city is always involved in the blackout. That's the first order approximation of the tail, and so it's a very rough approximation that all the other cities do not matter. You can instead of just a single biggest city, you can look at the top K cities and then do more refined, try to do more refined analysis. But I don't think that answers your question. But I don't think, like, if there is there is an inherent bias, because like if for the tail you only care about the big cities. So like a small city doesn't contribute to a big blackout.
So maybe, I guess, to be more precise, now that we're talking about it, maybe what I'm confused about is, like, when we talk about the quote unquote distribution of blackouts, I can imagine two ways to think about that. One would be roughly the number of blackouts doesn't really matter there. It's just a proportion. Like it's just somehow about the volume of units of watts lost.
Yeah, but yeah, that's what they do. So if you go to these data sets, they have recordings of certain events that got lost, that resulted into at least 15,000 people being shut off from power. So they compared to Europe, actually, the US is doing a great job there. They nicely record all those incidents. That results in a data set of like incidents where at least 15,000 people were cut off from power. And so like distribution of so I look not at the entire distribution, of course, but just at the tail, right? So and then I'm looking at the number of people that got shut off. You could also look into how much megawatts will be lost, but that will be, for the tail purpose, will be the same thing.
Okay, thank you.
Okay.
Okay.
Maybe one final question, and then it's my son's birthday.
Yeah, happy birthday to him.
Yeah.
Okay, so one.
I bought a mechanical computer for him, and I want to play with it. So now nobody wants to ask a question anymore.
Okay, so if no more questions, we will just let Bert go and play with that mechanical computer. Thank you a lot, Bert.
Okay, thanks so much. It was really a pleasure to do this. Thanks.
Yeah,
Bye.
thank you. So for the next week, it's the because of Labor Day, we're not going to have a talk, and we will continue the week after. Yeah, thank you, everyone.
Thank you.